So I'm not sure whether this will be new to you or not, but we've done a fair bit of implicit differentiation, haven't we?
Yes, we have. We have done that. So this would be...
Not quite that.
It's not the same thing, but it's not that far, is it? It's... Let's start with it, because I think I should have done it.
Oh, absolutely. No, I'm not saying dare we. I definitely think we dare, but you know, whether or not you've seen it before, but anyway, don't let me.
I'd imagine I probably have, but I couldn't immediately.
I think yes.
say.
I mean, there are all sorts of ingredients here that look familiar enough, which is great. But stop me at any time if you know, if I'm telling you stuff you already know. But I have a feeling you haven't solved a differential equation of this kind. You might have, and I was taking a second look at it just now, thinking, oh, is it as simple as this? Do we have the derivative of h with respect to t equals some function of t? In which case, we've done plenty of that. We could say h would be a matter of doing what?
Integrating that.
Integrating that with respect to t.
Yep.
But the spanner in the works is this h here. So we haven't got an explicit derivative explicitly in terms of t.
No.
So it does look like this is the result of an implicit differentiation, perhaps. Okay, because when we were differentiating implicitly, we often ended up with dy dx equals stuff to do with y as well as x, didn't it?
Yeah.
They were fractions mostly, weren't they? And you had y's in there as well as x's, because it was implicit. Sometimes we were able to get rid of the y's, but
often not.
Yeah. Now, to do this, then, we want to turn this straight away into something that we can look at as a simple reverse implicit differentiation.
Is that like would we reverse chain rule?
Yeah.
So, yeah.
You know, not in a terrible way. I mean, basically, we're just going to divide both sides by h, first of all. Okay, so we've got 1 over h times dh dt equals
divide by cos 0.25 t over 40. So yeah, just like that.
And then the right hand side is easy enough to integrate, isn't it? Now,
the right hand side, yes. You would
I mean, we could start with that if you like.
Yeah, we might as well. So would you get
integrating with respect to t, because it's a derivative with respect to t? Yeah. What would we have up the top?
We would have sine
0.25 t. Yeah.
T. Yep. And then
where a quarter t is the inner function. Yeah.
A quarter t is the inner function. Yep.
Okay.
So the integration of that would be differentiation of that would be
good.
0.25.
Yes.
So that would, the whole thing would have to be times by 0.25 on the bottom.
On the bottom, yeah.
Yeah, and then the 40th, well, basically that would mean what's, all right, okay, so that's a quarter times a 40th, which
is it? Careful.
Is it?
I thought you were putting 0.25 on the bottom.
I am. Oh, wait a second though, because yeah, no, you can't do that.
Basically, we want to do the reverse of multiplying by a quarter.
We want to divide. We want to divide by times by 4.
Yes.
So we want to, what times is by 4 to get a 40th? Yeah, well, yeah, the 4/4, so 1/10 on the top.
Yeah. And now we can check it, pretend we're differentiating that, and we would get that, where the 4 and the there and the quarter there cancel, don't they?
Mm-hmm. Yeah.
So that we can see the whole thing is secure, isn't it? If we differentiate that, we get that.
Mm-hmm.
So we've turned the right-hand side into an explicit integration, differentiation. It's all explicit, explicitly in terms of t.
Yeah.
If the right-hand side is in terms of t with respect to t, we want the left-hand side to be with respect to t as well, don't we?
Yes, we do. Right.
So can we figure out what would differentiate to give this with respect to t?
It's like a product rule. Is actually no, sorry, no, it's not. Can we figure it out? So dHdt. Ooh. H.
Let's test it. It's not a bad start. What would that differentiate to with respect to t?
dHdt?
Yes, just dHdt.
Yeah.
I mean, you might say, well, it's an inner function, and that would be a good idea. But if it was just h, then the bit that differentiates with respect to h would be just what? What would be the derivative of h with respect to h?
Nothing. Just 1.
Just 1. But then we would it would spew out the derivative of the inner function, you're right, and that would be dh dt, which is good. But we want the outer differentiation, the differentiation of the outer function with respect to all of h, to be 1 over h instead of just 1. Apart from that, everything worked fine, because if you identify the inner function as h, well, that's the implicit aspect of the original differentiation, which is fine.
Yeah. So we now need to work out what the is it sort of like yeah, so wait, so now what would we be doing exactly? So are we basically integrating 1 over h?
With respect to?
With respect to t.
Well, luckily I mean, if we were, that would be a problem, because we've differentiated the right-hand side with respect to t. But having the dh dt here means we can see that as the derivative of an inner function of a composite. So you were about to say, I think, is it reverse chain rule? Definitely. That's why I'm keeping there and that there.
Do you log? So you log h?
So just log h. It's going to work perfectly.
Okay. Log h. So log h equals a 10th sine 0.2.
Yes, with one crucial detail.
One crucial detail plus c.
Yeah.
Was that on both sides?
I see your point, but if you think about it,
actually, no, you don't have
if
to.
They both could be any constant.
Yeah, because c is just the leftover stuff you don't know. It's not specific values because you don't know how many there are.
Nicely put. Yeah.
Yeah.
Well, yeah. So, so here was our bottom row. 1 over h times dh dt equals all of that, which integrates to all of that. So we've solved a differential equation which wasn't simply, look, the derivative equals this function of t, integrate with respect to t, or
Mhm.
x or whatever. It was more complicated because of the implicit origin, the implicit differentiation behind it. But we've used the fact that we had a derivative of the inner function to get back up there with respect to t, after all,
Mhm.
via the chain rule.
Yeah.
So we've integrated the whole equation. We've solved the differential equation to get h as a function of t, potentially.
Yeah.
So they're saying, look, make h the subject, basically, and then we should end up
Yeah.
agreeing with them.
Right. That essentially means, well, that's not too far away, is it? Because it's just
Yes.
what's E? Is it just called E? How do you say that? I forgot the name.
E to the power of, yes, if you put
Yeah.
the whole of each side
E
as a
to
power
the
of
power
E,
of E. Yeah.
it's
Yeah.
hard
So
to say, but you can say it like that.
you'd
Each
get
side as a power
H
of E.
equals E to the power of, and then there's the rest just E to the power of a half of a tenth sine 0.25t.
Okay, so what should I be writing?
H equals,
Yes.
and then E to the power of
Yeah.
a tenth sine 0.25t plus C.
Where's the
Then
plus C?
up top
Yes, good, in
above.
the power.
Yeah.
That's crucial.
Mhm.
Okay, because actually when that happens, if you've got a, if the power is a sum, we know we can expand it, don't we?
Mhm.
So what will it look like then?
If the power is the sum, we can expand it e to the a tenth sine 0.25 t, and then that plus e to the c.
Is that what happens? If you've got e to the a plus e to the b, what's that?
Oh, it's ab. So
Is it?
no, sorry, that's multiplying. No, it's not. You have to. What do you do?
There's not much you can do. If you've got
There's not much you can do.
2 to the 5 plus 2 to the 8, you're going to have to add 32 to 256. There's no way
Yeah.
around
No,
it.
so there isn't much you can do. Yeah.
So
Okay.
this never happens. That will never expand, like nothing expands to that. You can't simplify that, you see.
No.
So that can't be right. How do we end up with a sum in a power? One thing plus another in a power.
One thing plus another in a power. Um. You multiply the two.
It's when you were multiplying different powers of the same thing, yeah.
Yes. So times e to the c rather.
Times e to the c, yes, certainly.
Yeah. Okay. What does the question actually want? What was the form it wanted it in?
Well, h equals, that's great, but notice they'll have got a bit further.
They got to.
But we haven't used all the information yet. So if we put, given that, this is probably the information we need, given that the passenger is 5 meters above the ground at the start of the ride, how could we put that information in here? The passenger's 5 meters above the ground at the start of the ride. What's eraser? Hang on a sec. Shift E, I see. Right. Pardon me.
If it's 5 meters at the start, does that mean it wants you to multiply by 5? No, sorry, no, add 5.
Well, we've got this information that 5 is a height at a particular time. The height is 5 when the time is
0.
yes.
Oh, so yeah, so make 5 equals 5 equals e to the 10. Oh wait, no, you don't even need that because something to the power of 0 is just 1.
Yeah, that's right. Because sine of 0 is what?
Sine of 0 is 0.
Good. So you've got e to the 10th of 0. So e to the 0 times e to the c.
1 e to the c plus 1.
Sorry, what does the right hand side say?
E to the 0. Oh, 0 times c. So e to the
0 times c.
no, 0 plus c. So e to the c.
Yes, true. That's right, because e to the 0 is 1, of course.
Yes.
I think you mentioned that.
Yeah.
So, but now by a different route, you're getting to the whole thing is just e to the c. Yes, I agree. So our full statement.
Oh, right. Now that makes sense. Yeah. Okay, that's where that 5 came from. H equals 5, and then e to 10th.
And then perhaps that is exactly what they had. Probably is.
Well, it can't be that far off.
Yes, indeed.
Yeah, it is.
They just put a decimal.
Well, that's...
Which was more consistent since we've left 0.25 as a decimal. Yeah.
True. It does make a difference, but I doubt they would ever mark you down for that. But
yeah.
Maybe at university or something they might, but I don't know. I've never been.
I don't know. I'd be willing to speculate, probably even less in that scenario. But anyway.
B. What was the second part of this? It's only a 1 mark, isn't it? Yeah. State the maximum height of the passengers above the ground. Well, it's when...
Yeah, we did something similar, didn't we, for the boat in the harbour?
We did. Essentially, we have to find what's the highest value of sine we can get.
Yes.
And that'll be the highest value, because anything, the greater the power, the greater the thing.
Oh yeah, that's right. Good.
So 0.25 times, well, the maximum that sine gets to is sine of anything gets to is 1, isn't it?
Good. Carry on.
So that means that 0.25 the max of sine gets to 1. So if you do 5 e to the 10th of 1,
exactly.
So 5 e to the 10th, is that the highest?
Absolutely.
Whatever that may equal.
Yep.
5.53. Yeah, 5.53. Okay, and then find the value of t.
Yeah.
Which is for the second time. So this is very similar to what we did yesterday, and that it's about the, well, if you want to think about it in terms of shape of curve, you can. If you want to think about it in terms of unit circle, you can.
Yeah, quite.
I don't have to guess to know which we're going to be doing. Because anyway, yeah, so...
Yeah.
Yeah, so essentially we want that value of...
I mean, on the unit circle, we would be it's a sine function, so we know the lowest. Oh no, hang on. We'd be starting when sine is 0 rather than at its lowest.
Yeah.
So actually, yes, it's just this situation again, isn't it? Do they want the second maximum?
The second maximum, yeah.
Yeah. Okay.
Right, so... Okay, well, if
in a
you
way,
try...
perhaps the simplest way is, sorry, yes? I mean, it is
no,
going to be 5 times the time of the first maximum. We can see from a diagram like that, can't we?
5 times. Oh, yes, yeah. Oh, that's a good way of that. Yeah, that works. So then, well, actually, does that just mean we can find the first? Yeah. So, the y coordinate of. Let me just think. What effect does the 0.25 do? It affects the y values, doesn't it? And does that multiply them by 4?
On this graph, it's affecting horizontally, isn't it? It's a horizontal scaling. But I think, you know, if we're considering it as 5 times the first result, well, that's when we reached from 3 o'clock up to 12 o'clock the first time, isn't it? On the unit circle.
Yes. So that means that that's the second time. So the angle would be 300. No, not 300. 360 plus 90, which is obviously 450.
Okay, so you're okay.
I kind of jumped, but
no. In a way, you're taking a detour. I mean, I'm thinking, why don't we just find the time from here to here, from 0 to?
Oh, does it want the time? Sorry.
Let's get the time for the first maximum.
Yes. Okay. Right.
And then multiply. I just think it would be worth doing it that way. So the first time we reach a maximum, we've reached a time of what on the clock? 3 o'clock is 0.
12 o'clock.
12 o'clock being what angle?
90 degrees.
Yeah. Sorry, I'm stating the obvious on that. But
yeah.
But what does that mean about what's happening here? So the first time h reaches a maximum is going to be where? What can we say about this side?
That equals 90.
What does?
The other side equals 90, so 5e.
The whole of it?
Oh, no, just the power.
The whole of the power? What is it that's reached 90?
The sine, the 0.25t.
Exactly.
0.25t equals 90. That is essentially what you're saying. So, yeah.
Yeah. Oh, is it degrees? Or we've been doing calculus, it's probably radians, isn't it?
It is.
That we need to be, they'll have given the domain in radians, I think. No, they haven't. Ouch.
Well, in which case
if in doubt, use radians,
it's pi
especially
over 2,
if you're doing calculus.
Yeah, it's pi over 2, though.
Think about that. Exactly, yeah.
Right, and then, that makes it actually easier for this bit because you get 4 pi over, you get 2 pi.
Yeah. Let's hope that's sensible then. So it's 2 pi.
5.
T is in seconds. Oh, but we're going to multiply by
10. No, by 5.
By 5, therefore
it gets to 10.
10 pi, which of course we can immediately approximate.
We can, yeah.
That far anyway, I can't go further than that myself.
Well, 31, neither can I, honestly. I'm not one of those people that's ever tried to learn.
So there we are. They wanted it in seconds,
Yes, well, is
and that looks
10
about.
pi is 10 pi seconds not a number of seconds? I don't know.
Oh, I see. Yes. Well,
I mean, it's probably better like that because
I think
it's
so. Slightly better. 31.4 seconds, and it seems realistic, doesn't it? You'd be at the top again for the second time, half a minute in.
yeah, that would make sense. Yeah. hmm Yeah, I don't see anything wrong with that. Okay. Yep. Right. So that question wasn't too bad. The first bit was just a different way of thinking about
Yes.
integration.
Oh, I haven't told you what it's called.
What is it called?
Separation of variables, and you probably see why. Because of the implicit origin of things, there was an H interfering with the T statement of the function, of the derivative function. We had to separate it out, dividing both sides by H, so we could deal with it like that.
Yeah.
Confession time, what you'll be taught to do, which you might prefer, is to say 1 over H times dH dt, but let's take the dt around the other side. Oh, okay, which doesn't quite make sense yet, unless we put an integral sign there and here. Ah. Oh, oh. Can I draw it? Yeah, like that. Now it says the integral of 1 over h with respect to h equals the integral of that with respect to t. So you're not really differentiating both sides with respect to t anymore.
No, you're not. Okay.
Even though you really are, because you're doing this, because you're working backwards through the chain rule on the left, really.
Yeah.
And
Well,
so you are.
yeah.
Sorry? Yeah, so
No,
you are differentiating both sides with respect to t, but you may well prefer this habit of, and this method. Writing that, and then writing the result of that integral equals the result of that integral.
I was perfectly happy with the first way, honestly, but
Fine.
if that way works, I'll keep that in mind as well.
Yep.
Okay.
Cool. Right.
Next.
Oh, was there something else? Separation of variables. That's what it's called. I mean, that is the only kind of differential equation that you need to know how to solve, apart from the explicit kind, which isn't. You wouldn't even refer to it as a differential equation, usually, do you? You don't say, "Oh, I'm solving a." If they tell you that the derivative function, say velocity, is this or that, the velocity equals the displacement varying with respect to time, rate of increase with respect to time equals this or that. Please find the displacement function. You would just integrate. And you don't think of that as a differential equation. You haven't called it a different differential equation, but in the sense that it's an equation with a differential in it, it is a differential equation. But it's overkill to talk that way. But this is a differential equation which you solve in that way. And other methods, of course, for other kinds of differential equation. But that's the only one you need in the syllabus. Right. So next.